Section 7.1, Adding and Subtracting Polynomials. First, let's start out with the definition. A polynomial is a single term or the sum of two or more terms containing variables in the numerator with whole number exponents. So here are some examples in the chart of what a polynomial is, and then we'll look at some examples of what a polynomial is not. So let's look at the first one, 7x squared minus 9x cubed plus 6. That is an example of a polynomial. In standard form, we rewrite the polynomial so that the term with the highest exponent comes first. So when I look at my polynomial, that term, the negative 9x cubed, that has the highest exponent. So that term needs to come first. Following that will be the 7x squared. So we will have plus 7x squared, and then the constant will come last. The degree of the polynomial is the highest power on the variable. Highest power on the variable. So in this case, the degree of the polynomial is 3. Now, when it says type, that refers to the number of terms in the polynomial. This polynomial has 3 terms, 1, 2, 3. So this is called a trinomial. Tri being the prefix for 3. Okay, let's look at the next example, 5 plus 8x to the 4th. So remember our pattern, standard form says the term with the highest exponent comes first. And since this is a plus 8x to the 4th, it starts with a positive 8x to the 4th, plus 5. The highest power in this case is 4. And since there's only 2 terms, this is called a binomial, bi meaning 2. 7x squared is our third one. Well, there's only one term, so the only way I can write it is 7x squared with a degree of 2, because the highest exponent is a 2. And there's only one term, so this is considered a monomial. And now let's look at the last one. I see 4 terms. The highest power is an exponent of 3, so that term comes first, but the negative sign goes with it, so it starts out negative 6x cubed. The plus 8x squared will come next. Then the plain old x term, that's x to the power of 1. And then my constant will come last. The degree, remember, is the highest power, so the 3 is the highest exponent. Now, this has 4 terms. Anything beyond 3 terms, we just call it a polynomial. So there's monomial for 1, binomial for 2, trinomial for 3, and anything beyond that is just poly. The prefix poly means many, so that just means many terms. All right, those are some examples of polynomials. Now let's look at some that would not be an example of a polynomial. So for instance, let's say I had 1 over x plus 2x. That would not be a polynomial because the x is in the denominator. Remember, we said the variables have to be in the numerator. We also need whole number exponents. So something like 2x to the 1/2 power plus 3x to the 1/4 power. Those are called rational exponents. We really haven't gotten into those yet in this class. But that's not an example of a polynomial, and we're only working with polynomials because 1/2 and 1/4 are not whole numbers. So these are non-examples, just to kind of give you an idea. All right, let's look at example 1. In example 1, we're adding the polynomials together. So really all we have to do here is combine like terms. So remember, like terms have the same variable and the same exponent. So for instance, everything with a power of 3, the x to the power of 3, I can combine. So the negative 11x cubed plus 16x cubed, I can combine those. Everything with a power of 2, I can combine. So the 7x squared and then minus the 3x squared. Everything with x to the power of 1. So that's a negative 11x plus 3x. And then the constants. So that would be a negative 5 minus 15. So I combine my like terms and that will give me my final answer. So negative 11 plus 16, that's 5x cubed. 7 minus 3 is 4, so this would be plus 4x squared. Negative 11 plus 3, that will give me negative 8x. And negative 5 minus 15 is negative 20. And now let's just clean it up. I don't need all those plus and minus signs in the parentheses. So this is 5x cubed plus 4x squared minus 8x minus 20. Okay, so that would be the sum, or that would be the adding of the polynomials. All right, let's look at number 2. Let's subtract. The first thing I'm going to do is I'm going to rewrite this problem, because remember, when you're subtracting a number, that's the same as adding the opposite of a number. So really what's happening is this negative sign is getting distributed to everything inside that set of parentheses. So this becomes plus, notice how that subtraction sign turned into a plus sign. Remember, subtracting is the same as adding the opposite. So now this becomes negative 2x squared, this becomes plus 4x, and that becomes plus 6. So by distributing the negative sign, I've changed the sign of everything inside the parentheses. Now I can combine my like terms. So I have a 9x squared plus a negative 2x squared. So 9 plus negative 2 is 7. So 7x squared. I have 7x plus 4x. So that's plus 11x. And then my constants, I have a negative 2 plus 6 is plus 4. So 7x squared plus 11x minus, I'm sorry, plus 4. Okay, let's look at example 3. Again, this is another subtraction problem. So the first thing I'm going to do is distribute that negative sign, which is going to make everything become its opposite. So the first parenthesis stays the same. This becomes plus, and then that becomes the opposite of everything inside the parentheses. So that's going to become negative 5y cubed plus 3y minus 6. Now I can combine like terms. So the y cubes, I have 8 minus 5, that's 3. Now let's look at my y squared. Nothing else over here is a y squared. So that minus 10y squared doesn't combine with anything, so it stays the same. look for y's. So minus 14y plus 3y is minus 11y. And a negative 2 plus a negative 6 is negative 8. So it ends with minus 8. So 3y cubed minus 10y squared minus 11y minus 8. All right, let's look at example 4. This is a little different. So we have two polynomial functions. F of x equals x squared minus 4x minus 2, and g of x equals x plus 1. Now, part A says find a new function called f plus g of x. Well, creating a function called f plus g of x means you take the f of x function and you add it to the g of x function. So f of x, I'm going to replace it with x squared minus 4x minus 2 from here, plus g of x right here, which is the x plus 1. Now I just combine like terms. There's no x squared in the other set of parentheses, so this is just x squared. So the minus 4x plus 1x becomes minus 3x. And then the constant, minus 2 plus 1, is minus 1. So my new function that I created is called f plus g of x. And it equals x squared minus 3x minus 1. Now let's look at part B. It says find f plus g of 1. Well, I already found f plus g of x. And remember, f plus g, that's just a new name for a function. Like I can call something f of x, g of x, h of x, a of x, b of x. Now I'm calling it f plus g of x. And I know that that equals x squared minus 3x minus 1. So now what it's telling me to do is it's telling me, okay, take that f plus g function you found, and now let's evaluate it for when the variable is equal to 1. So that means everywhere I see an x, I'm going to replace it with a 1. So I'm going to put in an open parenthesis for everywhere that an x will go. So 1 squared minus 3 times 1 minus 1. So that's going to be 1 minus 3 minus 1, which simplifies to negative 3. Okay, let's look at part C. Now I have to find f minus g of x. Well, we'll use the same reasoning as before. F minus g of x is the same as taking the f of x function and subtracting the g of x function. So my f of x function is x squared minus 4x minus 2, and I'm going to subtract my g of x function, which is x plus 1. So I'm going to distribute that negative sign, which becomes a plus, and then everything turns to its opposite. So that becomes negative x, and that becomes negative 1. Now I combine like terms. X squared is all by itself. I have a negative 4x plus a negative 1x, so that's minus 5x. And then I have a minus 2 plus a minus 1. So my final answer is x squared minus 5x minus 3. All right, part D, very similar to part B. I'm going to take my function I found. Remember, up at the top, I found f minus g of x, and I found that to be x squared minus 5x minus 3. Well, now, everywhere I see an x, I'm going to evaluate it for a negative 1. So everywhere I see an x, I'm going to open up a parenthesis and put -1 inside. So -1 squared, that's -1 times itself. -1 times -1, that's 1. -5 times -1 becomes +5. So this becomes 6 minus 3, or +3. Okay. Now let's look at an application problem, and let's just see an example of when we would use these polynomial functions. So in the year 2004, approximately 43,000 people died in motor vehicle accidents in the U.S. Does a driver's age have any relationship to his or her chances of being involved in a fatal car crash? So take a second right now and maybe just formulate an answer, a general answer to that question. Do you think a person's age has any effect on their chances of being involved in a fatal car crash? Okay, now we're going to work through the activity and we're going to see if there is a relationship. So number 1, to compare the fatalities of one age group to another, you must use some data. The number of fatal vehicle crashes per 100 million miles driven can be approximated by the following function. So you can see the function right there. X represents the age of the driver. Now, remember, input and output. Remember, X's were our input values, and the Y's were our output values. So part A says, what will the input values represent? So in this case, we're being told X is the age. So my input values represent the age of the person who's driving. So that means if I take this function and I plug in an age, that's an input, I'm inputting an age. My output is going to be the number of fatal crashes. So remember that magic pot we did in the classroom? Here's my magic pot. If I take an age, put it into the magic pot, out comes the number of crashes that people in that age group will get in. So I input age and out comes my number of crashes. All right, part C, it says, recall that the domain of a function is the set of all input values for a function. Or just remember, domain corresponds to all the x values. Input values, x values. What restrictions do you think there will be on the domain for this function? So that means, are there any x values that we're not allowed to use? That's what we mean by restriction. So let's go back. Remember that x stands for the age. So you want to ask yourself, are there any x values that wouldn't make sense here? Like for instance, negative x values? Why would I use a negative number for x? You can't have a negative age. I wouldn't want to find the amount of crashes for someone who's -5 years old, would I? How about 1, 2, 3? Would I want to find the number of crashes for a 3-year-old? No. Probably 16 is the first place where my x's are going to start. So for my domain, I'm going to say the set of all x's such that x is greater than or equal to 16. Now you might say, well, wait a minute, isn't there a maximum number? Does it go all the way to positive infinity? No. There's probably a reasonable number, maybe 80 years old, 85, 90 years old. But we can't really exactly say how old the oldest person is who drives. So we'll just say this in general to give it a good idea of what our domain is. So we can say greater than or equal to 16, or we can do it in interval notation, noting that we know somebody can't be infinity years old. We're just kind of giving it an estimate. All right, now we're going to find and interpret f of 75. So what that means is everywhere I see an x in the function, I'm going to replace it with the number 75. So looking up at the top, I have 0.013x squared. So inside that parenthesis is going to go a 75. minus 1.19 times x, and then plus 28.24. Okay, I'm going to do 75. All right. Exponents first, according to my order of operations. So the first thing that I need to do is 75 squared. So 5,625. Okay, and then I can do this multiplication next. I can do the 1.19 times 75. Gives me 89.25. And then plus my 28.24. Okay, so next I'm going to multiply again. 0.013 times 5625, 73.125, minus 89.25, and then plus 28.24. So now I just go left to right and do my subtraction and my addition. So 73.125 minus 89.25, and then add the 28.24. So I get 12.115. So remember, that represents the amount of car accidents. So I'm going to estimate, I'm going to say that's about 12. So I would say there will be about 12 fatal car crashes for every 100 million miles driven by, now do you remember by who? Who's doing this? The 75-year-olds. That was how I would interpret it. Notice it said find and interpret. So that would be my interpretation. Okay, let's see what else we got on the next page. Oh, another one. Find and interpret f of 20. So I'm going to do the same thing. So 0.013, this time it's going to be times 20 squared minus 1.19 times 20 plus 28.24. Okay, so I would advise you to try this on your calculator. Make sure you can get it. Maybe pause the video, but make sure that you can arrive at the correct answer of 9.64. So we'll say that's about 10. So to interpret it, I would say there will be about 10 fatal car crashes for every 100 million miles driven by 20-year-olds. Okay, so now you can kind of go and think back to your prediction. Did you have a prediction at the beginning? Did age affect the number of car accidents? So we found 75-year-olds would get in about 12, 20-year-olds would get in about 10. Okay, let's keep going. Let's go back to F. Do you think there's a relationship between the age of a group of drivers and the amount of fatal accidents caused by drivers in that age group. And then let's explain. So, if you look at it, 20-year-olds got in 10 car accidents, 75-year-olds got in 12 car accidents. So you might think, okay, well, as you get older, the number of car accidents you get in goes up. But is it that simple? If 20-year-olds get into 10 fatal car accidents, do we think 30-year-olds, 40-year-olds, they get in more? No, probably not. You start out young and you might not realize the dangers of driving. You might not be as responsible as maybe you should be. You know, you might not see all the different factors that go into driving and how defensive you need to be. So you might start out maybe getting into more car accidents than you'd like. But as you get older, you probably get more responsible. You realize there's more consequences, you know, if you get in accidents. So probably as you're 30, 40 years old, maybe the chance of you getting in an accident goes down. Well then, on the other aspect, you do get older, 50 years old, 60 years old, 70 years old, people start losing their reaction time, and so it does kind of make sense that there would be more accidents on the upper end of the ages as well. So, it can't just be as simple as this. All right, so let's go down here. Let's make a sketch of what we think it would look like. Okay, I'm going to take our function, write it down. So we had 0.13x squared minus 1.19x plus 28.24. Now this is not linear, so I can't just graph the slope and the y-intercept like I would if it were a line. Notice I've got this squared. But I still can find the y-intercept. That is one part that will be the same. By plugging in 0 for x, I can find the y-intercept. Okay. So basically these would go away. So what that means is that the ordered pair 0, 28.24 is on my graph. So let's just roughly number this 5, 10, 15, 20, 25. I'm going off a little bit, that's okay. We'll say 30 is up here. Okay, so 0, 28.24. That would be up here somewhere. Well, let's think about what that means. That means if someone who's 0 years old is driving, they'd get in 28 car accidents. Remember, we restricted the domain. So granted, that point doesn't really make sense. It just kind of gives us a place to start. Okay? Let's go back up to the 20-year-olds. We said 20-year-olds would get in about 9.64 car accidents. Well, hey, there's an ordered pair out of that. 29.64. Okay, so let's, on our x-axis.
Okay, you sneaker.
So on the x-axis, let's go by fives. So 5, 10, 15, we'll say that's 20 years old. 25, 30, 35, we'll say that's 40 years old. 45, 50, 55, let's say 60 years old, and let's keep going, let's get those 75-year-olds in there. 65, 70, 75, 80. So we'll say those are 80-year-olds. Remember, X was our ages. All right, so 20 and then 9.64, so that's going to be probably there somewhere. And then remember, we also had 75-year-olds getting in about 12 car accidents. So 75-year-olds in about 12 car accidents, so they'd be about here somewhere. So if you think about what we said that your number of accidents will go down and then it'll kind of change direction and go back up. Okay, let's just find one more age group. Let's find these 40-year-olds. Let's see what these guys do. Okay, so I'm just going to type it on my calculator. So it's 0.013. Let's put in 40-year-olds. And plus 28.24. 1.44. So 40-year-olds, if we rounded to the nearest whole number, we would say they'd only get in about one fatal car accident. So that's going to be way down here. So you can see what's happening. The number of car accidents decline as you get older, and then you hit a point somewhere around 40 years old where you're pretty good, you're pretty responsible, you're not getting into too many car accidents. And I don't know if this is exactly the bottom, I'm just estimating to get a good shape of the graph. But then as you age, like we said, reaction time may slow down, and we might get into some more car accidents there. So we can see it dips, and then it goes back up. So that's an example, and that's actually a really good example of an application of a polynomial function. So you can see not everything is a straight line. There's different patterns. In this case, it definitely had a different pattern than the linear graphs we're used to.